Today we're going to talk about the derivative and what that means, especially as related to everything we've been talking about recently. So before we get into what the derivative means, we are going to recall what we've been doing the last couple days. So the first is to estimate the slope of the tangent line to the graph of f of x equals x squared plus x at x equals 2. So remember, when we're estimating the slope of the tangent line, we're going to choose an x value close to x equals 2. So remember, when we were doing this yesterday, we were choosing values that were like 0.001 away, so we'll do the same here. So the value that we're going to choose to plug in here is x equals 2.001. You could pick 2.0001, 2.000001, but for our purposes, we're just going to choose this. So if we look here, we have f of 2.001 minus f of 2 over 2.001 minus 2. Remember, that's our slope formula, y2 minus y1 over x2 minus x1. And so if we put that into our calculator, we'd be plugging in the 2.001 into x in both of those places. So that would be giving us, when we calculate that, 4.001, approximately 4 would be our estimate. So that is our estimate for the slope of the tangent line to f of x when x equals 2. So the next thing that we're going to do is find the actual slope of the tangent line to that function when x equals 2. And so to actually find the slope, that's when we're going to use the limit. So the limit as h approaches 0 of, remember, this is where we're going to do f of 2 plus h minus f of 2 over h. And again, remember that the 2 is coming from the fact that that is the x value that we're trying to approximate near, and h is going towards 0 because we're trying to get closer and closer and closer to exactly whatever that slope is at 2. So when we evaluate this limit, we're going to plug in 2 plus h into our function. So that would be 2 plus h squared plus 2 plus h, and then we're going to plug in 2 into our function. So plugging in 2, we have minus, that'd be 2 squared plus 2. So we have our f of 2 plus h, and then our f of 2 all over h. So then we have the limit as h approaches 0. If I multiply that out, that gives me 2 plus 4h plus h squared plus 2 plus h minus, that gives me 4 plus 2, which is 6, and that's all over h. So simplifying again, I have h squared plus 4h plus h, which would be 5h. And then I have, sorry, this should be a 4 here, 4 plus 4h plus h squared, 4 plus 2, which is 6, and then minus 6. So that drops out here. 4 plus 2 is 6, minus 6, and then it's all over h. So then I can factor out my h in the numerator, and when I do that, then this simplifies to just the limit as h approaches 0 of h plus 5. So then plugging in 0 for 5, I find that my approximation here, or excuse me, my actual value here of my slope of my tangent line is 5. So that is our actual value. It is relatively close to our approximation, which was 4. So what we're going to do is now formally define the derivative. So the definition of the derivative is the slope of the tangent line. So when we say that we're finding the derivative, we're finding the exact slope of the tangent line to a curve. It's also known as the instantaneous rate of change. We write it as f prime of a equals the limit as h approaches 0 of f of a plus h minus f of a over h. If that limit exists, then we say that f is differentiable at x is equal to a. So a couple of things. This is the instantaneous rate of change at a specific point. It's the slope of a tangent line at a specific point, and it's at whatever x value we're using here. So in this case, we're talking about a because it's saying f prime of a. So that's the x value at which we are finding our actual instantaneous rate of change, our slope of the tangent line. So again, the way that we say this, you see how this is f with a little apostrophe there? The way that we read that is we say f prime of a. That's how that's read. So I want to look back at the two examples that we did up here, and now knowing the definition of the derivative, there's a couple of things for us to look at. So the graph of this function, it would look something like this. And so when we have a quadratic function like that, then we can say that our limit at an x value is going to exist, right? So like, let's say x being 2 is here. The limit as we approach from the left and the limit as we approach from the right is the same because a quadratic function graph is continuous. And so we know that that limit is going to exist. So since the limit exists, we can say that our function f of x is differentiable at x equals 2, which means when we found this answer of 5, we found 5 to be the value of f prime of 2. So those are just a couple of little notes that apply to what we were just doing. So now we're going to use that definition of the derivative here in example 3. This explicitly says to find the derivative of f of x, and they're giving us the function negative x cubed, and we're finding the derivative at 3. So it means we're finding f prime of 3, and that's going to equal the limit as h approaches 0 of f of a plus h, where a is our x value. So in that case, it's 3 plus h minus f of a, which in our case is 3 over h. And so just like we have been doing, we're going to plug these values in to evaluate them in our function. So we have negative 3 plus h cubed minus negative 3 cubed all over h. So to simplify this, to multiply this out, we have negative whatever that 3 plus h cubed is. So we can think of it as 3 plus h times 3 plus h times 3 plus h. So this first set, when we multiply that out, would be 9 plus 3h plus 3h plus h squared. And then if we combine our like terms there, you have 9 plus 6h plus h squared. And multiplying that by 3 plus h, then we end up with 27 plus 18h plus 3h squared plus 9h plus 6h squared plus h cubed. So that is what we have here. And I'm going to actually combine some like terms here. So I have my 18h and my 9h. So those would combine to give me 27h. And then I have 3h squared and 6h squared, so plus a 9h squared, and then plus an h cubed. And then I have minus negative 3 cubed, so 3 times 3 times 3, 27, all over h. And so simplifying a little more here, these are all going to be negative when I distribute my negative, so I'm going to reorder them as well. So I have negative h cubed minus 9h squared minus 27h, and then I have negative 27 minus negative 27, which would be 0, and then this is all over h. And so if I factor out that h in the numerator, simplify with the h in the denominator, then I end up with negative h squared minus 9h minus 27. And so then at this point, if I were to plug in 0 and find the value of my limit, then I end up getting that my limit is equal to negative 27. And that is the value of f prime of 3. So the instantaneous rate of change for our function at 3 is negative 27. So for number 4, it says find the equation of the tangent line to f of x equals negative x cubed at x equals 3. So if we're writing the equation of the tangent line, it's the equation of any line. So to write an equation of a line, we need a point and your slope. So if we have a point in the slope, then we can use point slope form to write our equation of our line. You're going to find that we're going to use point slope form very frequently throughout this course, much more so than slope intercept or standard form. You're going to see point slope form with regularity. So remember that m here is your slope and x1, y1 is your point. So we are going to find our point first. So the first step, we're going to find the point. And to find the point, we already have x. X is equal to 3. So if x equals 3, then we're going to plug in 3 and find what f of 3 is. So that would be negative 27. So our ordered pair for our point is 3, negative 27. Then we need our slope. Well, to find the slope of the tangent line, remember that that's the derivative. So the slope, that is the derivative at x equals 3, which we already found. Remember that our slope of our tangent line that we found, f prime of 3 that we just found in example 3, was negative 27. That's, again, from example 3. So then the last step here is for us to write this equation of the line. So we're going to use our point slope form. So y minus y1 equals m times x minus x1. So plugging in, we have y plus 27 equals negative 27 x minus 3. So that is a perfectly acceptable equation of a line. It is written in point slope form. You can use that. If you really want to see what this would be in your slope-intercept form that you're used to seeing, you are welcome to multiply this out. And if you do choose to do that, it's just important that you remember that when you multiply something out and make that decision to do so, if you were to make a mistake in this portion of the problem, you would lose points for your answer. So generally speaking, you're better off leaving it in the less simplified form of point slope form so that you avoid making a silly mistake in trying to get to slope intercept form when the point slope form is perfectly acceptable. So let's refresh on what we just talked about. So to refresh, what is the difference between the average rate of change and the instantaneous rate of change? Well, there's a couple things, right? The average rate of change is the slope of the secant line, and it's the average of two x values and two y values. Right, so you're looking at the change over two different x values and two different y values. So the average rate of change for the interval here, this would be finding from 0 to 3. It's on that interval that we would be finding that average rate of change. If we look at the instantaneous rate of change, it is the slope of the tangent line. So remember that we have these other ways to remember this. So it's the slope of the tangent line for the instantaneous rate of change. We also call that the derivative, and we also call it f prime of a. So these are all talking about the same thing. So if we look at this graph here, we are going to call this graph, the first one here, g of x, and we're going to call this graph here f of x. And really quick, let's just check to see if we're understanding this. So our comparison here, which is larger, so is g of 0 or g of 3 larger? And so g of 0 would be the y coordinate here at this point, that's at 1, 2, 3, 4, 5, 6, and g of 3, that's down here, that's at 2. So which is larger? G of 0. Let's compare which is larger. Again, but this time we're going to say g prime of 0 or g prime of 3. So g prime of 0, that is the instantaneous rate of change at 0. So the slope of the tangent line at 0. So here's the slope of the tangent line at 0. It's negative, pretty steeply negative. And then here's the slope of the tangent line at 3. Also negative, but not as steeply negative. So which one is less negative would be the larger. And in this case, that would be g prime of 3. And a last quick check here. We're going to find the average rate of change for the interval 0 to 3 of g, so using g of x again. So if we're finding the average rate of change for g of x over the interval from 0 to 3, that's where we're talking about we're finding it over two x values and two y values. So our average rate of change here, that's the slope of that secant line. So we can look, we can see we're going down 4 and to the right 3. So the average rate of change there is negative 4/3. And then last, I want to see what is the average rate of change, what is the instantaneous rate of change when x equals 4. So when x equals 4, it's our slope of our tangent line. And so if we look at when x is equal to 4, that's right here. The slope of our tangent line is 0. So a quick little recap there for us. So now if we look at example 5, this gives us a function f of x equals x cubed minus 4x, and we have the graph here for us. Part A says, where is f prime of x approximately equal to 0? So this is saying, when is the slope of the tangent line 0? Or another way to think of it is, where is the tangent line horizontal? So if we look at our graph and we think about drawing in some tangent lines here, one place where we would have a tangent line that is about a slope of 0, approximately horizontal, would be here. And another place where that would happen would be about here. Those are the places where our horizontal tangent line exists, where our slope of our tangent line is 0. So we're going to approximate those x coordinates. So this is happening approximately, let's call it negative 1.25. And the other place where that's happening, we'll call it approximately 1.25. Are the approximations for where f prime of x is equal to 0. Then it says, where is f prime of x approximately equal to 3? So for us to have approximately a tangent line slope of 3, so the slope of the tangent line is 3. That's what we're looking for. So we want to look somewhere on our graph and see where are we going approximately up 3 over 1 if we were to kind of continue along the curve. So if we look here, that would not have a slope of 3. That looks more like we're going up 2 over 1, but somewhere relatively close to there might work. So let's see, if we were perhaps about here, then that would give us perhaps a slope of 3. So looks like we're going about up 3 over 1. So let me clear that out a little bit here so we can see it a little bit better. So if we're looking here, right about here, I would say, right about here. So if I draw in a tangent line there, it looks like we're going up 3 over 1 with that tangent line, which is what we want. And so that's happening right about 1.75, I would say. So that's happening at x equals 1.75. And then let's look over here on the other side to see if that happens anywhere. And so then if we look probably around here, we'll see the same thing happening. And that's at x equals negative 1.75. So something that you might notice here is that we have these opposite x values where they have the same slopes. And so this is actually a rule that happens with odd functions. So if f of x is odd, then f prime of a is equal to f prime of negative a, meaning they have the same slopes at a and negative a. So let's look at what that means. So an odd function is something like what we saw here in this problem. So an odd function is symmetric about the origin, meaning if you were to mirror one half of the graph, so for example, mirroring this side, if you were to mirror that across the x-axis and the y-axis, it gives you the other half of your graph. That's what it means to be an odd function. Not just that the degree is odd, but that the actual graph itself is symmetric about the origin. So if that's the case, then you can look at your function at, say, a and negative a, and if you look at the slopes of those tangent lines, you will see that they're the same. Or if you were to look here at this point and this point, notice that the slopes of those tangent lines are the same. So there's a similar rule for even functions. If f of x is an even function, then f prime of a is equal to negative f prime of negative a, which means that they have opposite slopes at those different x values, so at a and negative a. And so an even function could look something like this. An even function is symmetric about the origin, or excuse me, about the y-axis, whereas an odd function is symmetric about the origin. So symmetric about the y-axis just means if you were to take this side of the graph and mirror it across the y-axis, you would get the other half of your graph, and that's what we have here. So it's symmetric about the y-axis. So if I look at, say, this value and its opposite over here, notice that this one has a slope like this, and this x value has a slope like this. So they're equally steep, but going in opposite directions. They're opposite slopes. I hope that that helps you understand the basics of the definition of the derivative. If you have questions, please reach out to your teacher.